So, come to the end of the day and alcoholic activities. Now we have our first keynote. Now we have our first keynote speaker of the symposium. But first, we have a video from our sponsor. This is the video. From enabling our warfighters to navigate the most challenging domain in the world to facilitating scientific breakthroughs in space exploration, L3Harris is investing in technology that will change how we operate in space. Through creative and innovation, L3Harris continues to develop rapid solutions to address their partners' most complex mission needs, now and in the future. L3Harris, fast changes everything. So Harris, thank you very much for sponsoring this session, this talk. Our keynote speaker will be introduced by Myra Montos from L3Harris. Oh, there you are. I know.
Thank you so much for doing my job.
Around.
Thanks. I was lurking. Thanks for doing that. Now I can chop off like a full paragraph of my presentation. So good afternoon, everybody. As many of you know, my name is Myra Montrose. I am the Senior Principal for Civil Space at L3Harris. I recently retired from NASA. I worked in SMD for about 6-7 years, but I had a long history at NASA before then. And I selected L3Harris as my new employer because it's a pioneer in space, as you saw in the video. L3Harris instruments have been used in weather monitoring for over 60 years, and our optics are in many of the large space telescopes like we've heard. It's in Hubble, it's in Webb and Roman. So I am really very excited to be part of that company, but most excited about introducing our keynote speaker today, Dr. Catherine Cowan, NASA's chief scientist and the senior climate advisor. I met Dr. Cowan recently at the GOES launch, and I mentioned to her that I had the privilege of working for 3 of her predecessors. I used to be the executive officer to the NASA chief scientist for 5 years, one of the jobs I held the longest in my career. But unlike them, Dr. Cowan has that dual role. As chief scientist, she advises NASA leadership on science programs and science-related strategic planning and investments. And as a senior climate advisor, she provides recommendations for NASA's climate-related science, technology, and infrastructure programs. Dr. Cowan joined NASA as an IPA from the Pacific Northwest National Laboratories Joint Global Change Research Institute here in College Park, where she served as an Earth scientist. She worked in the Institute's Global Change Analysis Model, a system for exploring and analyzing the relationships between human and Earth systems in the context of global climate change. I think that is so fascinating. I would love to hear much more about that. She also worked on the Department of Energy's Energy Exascale Earth System Model, which is a system for analyzing the past, present, and future state of the Earth system. Her research simulates the interaction between global resources, focusing on the impact of land, water, and energy use through an environmental and socio-economic lens. Again, I'm so excited by that. It just brings together everything we need to know about our future and prosperity. In her almost 14 years at the Institute, Dr. Catherine co-authored an impressive over 100 publications. Her recent publications have investigated growing populations against agriculture and water scarcity in the face of climate change. She served on the National Academy of Sciences Committee on Models of the World, which created models for interrelated global systems such as economics, politics, and environment. She has contributed to the 3rd U.S. National Climate Assessment and 2 of the special reports by the IPCC, with 2 more scheduled for publication in 2022. There's so much more here that she has done. She received her PhD in Management, Science, and Engineering from Stanford University and her bachelor's in Computer Science and Mathematics from the University of Maryland. Go Terps! Without further ado, Dr. Catherine Cowan.
you for that introduction, and thank you for having me here. It's really nice to be back in College Park. This building was not here when I was a student, but it is beautiful and I'm excited to be here and to talk to you. As Meyer mentioned, I am the Chief Scientist and Senior Climate Advisor for NASA. And what I want to do today is really focus quite a bit on climate. I know you spent most of your day talking about James Webb, but I would like to talk about what NASA is doing for climate. I'll sprinkle in some broader science as we go. Is this the right thing to do?
Just tell them to switch slides.
Oh, there we go. Okay, so why climate? So first, we know from observations made by NASA and other organizations around the world that climate is changing. The animation I'm showing you here is temperatures, changes in temperature. It started from the late 1800s, and the animation is going to go through present day. 2021 was tied for the 6th warmest year on record, and the 8 past years have collectively been the warmest years since modern record keeping began. On average, temperature change in 2021 globally, global average temperature change was about 1.9 degrees Fahrenheit warmer than the late 19th century average, but we see larger increases in temperature over land than over ocean, and larger increases in the high latitudes, as you can see from this figure, than over the lower latitudes. Temperature isn't the only thing that's changing, so as climate warms, we also see changes in the rest of the Earth system, like the water cycle. So there's more heavy precipitation events, more floods, and more droughts. There's changes in Arctic sea ice, the extent and the thickness, increases in sea level, and more extreme events like heat waves and wildfires. And what we know from science is that those changes are due to increases in greenhouse gases from human activities. Science also tells us that how much more warming we'll get in the future depends on how much more we emit. As warming increases in the future, though, we can expect some of those changes I described to increase. So we'll see more frequent and intense heat waves and heavy precipitation events, and in some regions, more droughts. We'll see increases in the proportion of intense tropical cyclones and continued declines in Arctic sea ice, continued increases in sea level rise. So what is NASA's role in climate? So NASA is a US space agency that provides end-to-end research about our home planets. We have observations, models, applied sciences, and technologies. For observations, we use the unique vantage point of space to see the Earth and its features. We have more than 24 satellites and instruments in orbit, including several on the International Space Station. They can tell us things about clouds and precipitation, temperature, changes in the mass of ice sheets, changes in the amount of water stored on Earth, carbon dioxide, vegetation, and much more. And since we've been looking at the Earth for decades, we can see not just the state of the Earth today, but how it's changed over time. In addition to observing the Earth, we also develop technologies that can help mitigate or adapt to climate change, like sustainable aviation technologies. And I'll talk more about those later. We provide information that helps aid in disaster response and informed planning. So for disaster response, we work with response agencies and local decision makers before, during, and after disasters occur to help provide Earth observations and applied science and modeling results to inform the decisions they might have to make. Just as an example on that, for wildfires, we can see where fires are burning, we can see the burn perimeters and burn scars, we can understand more about the emissions associated with fire and the air quality effects those might have. We can look at things like soil moisture to get a sense of the fuel for fires. And we provide this information in as near real time as possible through our disasters mapping portal. In terms of planning, one of the things that's important about planning is thinking about where you might go in the future. And we use climate models for that. And it was interesting to hear both of the last two panels talk about modeling. And that's something we've done in earth science and climate science for a while. So the models at NASA and other organizations around the world can help us understand how the future might evolve in terms of climate. Just as one example of where we can give this kind of information, we have a sea level rise portal, where you can look at places along the coast of the US and it'll tell you both how sea level has risen in the past, including what's contributing to that, like thermal expansion or ice sheet melt, We can also look into the future, and this is a collaboration with other agencies and modeling centers around the world to provide information on projections of future sea level rise. So you can get a sense of where that might go. All of the data that NASA collects is freely available to the public, but we're working to make this more accessible. So we're working to make climate change more accessible for researchers, planners, and individuals in vulnerable communities. And this includes making things more transparent and open. So sharing not just the end state result, but also the tools and models we've used along the way. And one of the things I really enjoyed watching in the last couple of months is on James Webb Space Telescope, where we didn't just show the launch and the final science images this summer, but we're showing what's happening along the way, the selfies used for calibration and some of the alignment process. And we're working at NASA to do that throughout our processes, so people can see what we're doing along the way, and then try to make it more easy to reproduce and use the information that we're providing. At the same time that we're researching climate change, our facilities are also impacted by climate change. So we have a lot of facilities along coasts and low-lying regions that are vulnerable to sea level rise and coastal erosion and flooding events. We have centers out in California that are vulnerable to wildfires and droughts. And so we're thinking about climate change in our own operations as well. We have a lot of science missions underway, and I'm not going to go through all of them on this slide, but I did just want to make a few points about some of these science missions. First, I mentioned that we have a long history of collecting information. So just as a concrete example of that, we launched Landsat 9 in September. So we have about 50 years of records from Landsat program. And Landsat gives us information about land use and land cover. So you can see where there are urban areas and infrastructure, where are forests, where are snow. And because we have decades of this information, we can see how land use and land cover have changed over time. So you can see when you look through that, you can see expansions of urban areas and declines in forests around the world. This is really important for climate. Things like changes in forest cover matter in terms of emissions of carbon dioxide and also how much carbon we absorb from the atmosphere. Changes in built up land and snow cover affect the reflectivity of the Earth's surface, and so how much heat is exchanged and how much we warm through biophysical factors. We also partner, so the second point I want to make on this slide is about partnerships. We work with other agencies and international partners. In terms of other agencies, the Landsat program I just mentioned is a partnership with USGS. So we work closely with our other agencies and international partners around the world. One of the other interesting discussions that was started in one of the previous panels is about what we can, interdisciplinary and transdisciplinary science and what we can learn from other disciplines. And so I just want to highlight a little bit on the non-Earth science missions and what we learned about Earth from them. So we have a lot of heliophysics programs that are designed around understanding the sun. Well, the sun matters for Earth. It's a source of light and heat. It's also a source of solar winds, which means implications for space weather. And space weather affects electronics and satellites and operations on Earth. One of the ongoing missions in heliophysics, the Parker Solar Probe, is working to fly through the outermost layer of the sun's atmosphere to better understand the origin and evolution of solar winds. It's using Venus's gravity, and so it's doing some flybys of Venus where we can get some imagery of Venus. And Venus is actually really interesting from an Earth science perspective because it was once likely to have been a blue planet with liquid water. And now it has a really high concentration of carbon dioxide in its atmosphere, and it's really hot on the Earth's surface. And some of the research into Venus decades ago on the greenhouse gases and ozone on Venus have informed our understanding of the greenhouse effect and ozone depletion on Earth. The drivers are different. On Earth, greenhouse gas effect and ozone depletion are related to human activities and emissions associated with those human activities, but we can learn from the processes of other planets and inform that about what we understand about Earth. We also live in work and space. So the International Space Station has been operating for more than 2 decades, and on board station are several Earth observing instruments. So the instrument like OCO is the Orbital Carbon Observatory. It observes carbon dioxide concentrations, which is really important for climate and understanding Earth. JEDI is giving us a 3D profile of forests. So you can see the height and the canopy structure. And that's really important for understanding how much carbon is on Earth and vegetation dynamics. Landsat can tell us where a forest is. JEDI can help us understand what that forest looks like. In addition to observing the Earth from the space station, we also live on there, and some of the environmental control and life support systems and other activities on the space station have implications for Earth. So one example there The water processing and recycling system on the International Space Station has been used for ground-based filtration systems on Earth to help provide clean water in parts of the world that doesn't have it. We grow crops on the International Space Station. Some of the research by NASA scientists into growing crops has value on Earth and has been used on Earth. So a couple of examples there, some of the LED lighting is now used in indoor agricultural facilities on Earth. There's a research with help from NASA research, a fertilizer formulated with help from NASA researchers is helping release nutrients to plant roots at the rate they use them. And on Earth, that means less runoff into rivers and lakes, which has important implications for air quality. I mentioned earlier that we have sustainable aviation. So our aeronautics team has been working for decades with industry to help reduce energy use and emissions associated with aircraft. We work in advanced technologies, efficient operations, and sustainable fuels. Just a few examples there. We are working with the FAA and industry partners on air traffic management tools, which can help put aircraft onto flight paths optimized for minimal environmental impact. We're also working on new technologies like testing an all-electric airplane later this year. This will be a test of electric propulsion and battery technologies on aircraft. We have a lot of really exciting Earth science launches coming up this year. So just to highlight a few, Tropics, which will be this spring, is a set of 6 satellites that will help us better understand tropical cyclones, looking at precipitation and humidity at a very fast rate. Emit is an instrument that's going on the International Space Station later this spring, and it's going to look at mineral dust. And mineral dust has a really important role in both local climate and air quality. So the amount of mineral dust, it reflects energy from the Earth's surface back to space, and how much you have affects that absorption and reflection. It also has implications for air quality, which matter for human health and ecosystems. In November, we're going to be launching a satellite called SWOT, there's Surface Water and Ocean Topography. And this is going to give us more information about fresh and salty waters on Earth's surface. And Mira asked earlier about my research, and so a lot of the work I was doing was around water scarcity. And looking at how that might change in the future. And water scarcity, you need to understand how much water you have today and how much you'll need. So we use a lot of water for agriculture, to grow crops, and to produce energy. And the work that we were doing there, we were relying on, we needed a survey of how much water is running through rivers. And what you have right now is you have stream gauges for selected rivers. And then you use models to fill in the gaps. What SWOT's going to do is give us a global survey of the water in the river. So it's really important for understanding water scarcity and how much water we have available. SWOT will also give us quite a bit of information about oceans and ocean circulation. And oceans absorb quite a bit of carbon and heat from the atmosphere. So the surface ocean absorbs it and then it mixes. And how much more you can absorb of heat and carbon depends on that mixing. And SWOT will give us more information about mixing and help us improve models of oceans. We're also working in the formulation phase of the Earth System Observatory, and this is a set of satellites that are going to work together to provide a 3D holistic picture of the Earth. So it'll help inform things about climate change, agriculture, wildfires, and other Earth system dynamics. One of the panels I was in earlier was talking about what the decadals are. This is coming out of the Earth Science Decadal Survey. They've guided the direction that we'll go in this. And one of the first parts of this satellite, or this observatory, is going to be a satellite called NISAR, which is in partnership with the Indian Space Research Organization. And the NISAR is going to let us look at changes in the Earth's surface up to 1/2 inch, which will give us information about really complex processes like ice sheet dynamics, ice sheet collapse, or natural hazards like landslides and earthquakes. I am also, in addition to serving as senior climate advisor, I'm also chief scientist, so I like to highlight some of the non-Earth science when I talk about climate. I would love to talk more about Webb, but you guys have had a whole day on it, so I'll just say that I'm really excited for the science images, and I'm really enjoying following its progress along the way and hearing from your discussions about how we got here and where we might go in astrophysics. I'm also really looking forward to Artemis. If you haven't been following, we have a new program to put humans in robotics to explore the moon in preparation for missions to Mars. And Artemis 1 is the first of these missions. It's in a series of increasingly complex missions. So Artemis 1 is going to be uncrewed. It'll help us test the Integrated Space Launch System, or SLS, and Orion spacecraft. It'll also give us really important information about radiation. So as you move outside of low Earth orbit, there are different requirements, and so increased radiation, which affects crews and electronics. There are several science payloads on board Artemis. So many of them are related to this radiation question, but there's also things that are going to help us better understand the lunar surface. We'll have infrared imaging of the lunar surface and other lunar science capabilities aboard Artemis 1. Just in terms of status, it was rolled out to the launch pad for wet dress rehearsal was last week, and we'll know more about the specific launch date after wet dress rehearsal, but no earlier than May. And so I'll just wrap up so I can take some questions with just what's next. So this is just a summary of what's coming up in 2022 in terms of NASA and climate. So we have lots of Earth science missions coming. We're testing an all-electric airplane. We're continuing to provide Earth observations and applied science information to those who need it, and we're working to make that data more accessible.
Thank you. That's, I followed it, man, I followed it. Not so much. The questions. Laura, do we have any questions, Catherine? Right here. Somebody else see, everyone together. Anything online, Abigail?
Thanks for your talk. The Earth Systems Observatory missions are, to what extent are those adding new capabilities that we don't have today versus replacing some of the aging systems that we have observing Earth science objectives today?
So we're in the formulation phase now, so working through some of the details, but they're guided by the decadal survey, which raises some of the important science questions about climate and Earth science, and that's what's steering them. So a lot of the ones on like clouds and precipitation and aerosols are trying to help us better understand and narrow uncertainties in future climate change.
Miller?
I'm standing between them and the reception.
Thank you for your talk. I have a question. With all of the data we're generating and the dozens of satellite systems that are in operation today, each generating their own data sets, it seems to be a huge challenge in trying to do data synthesis and data alignment. What's the current initiatives within, at least your awareness, how are you going to approach the problem of actually making the data talk to each other?
Yeah, so that's an important, with any sort of integration of information, there's always some challenges associated with it. And I think there's quite a bit of experience within NASA doing this, like I mentioned, some of the disaster work that's integrating satellite information and models and tools and trying to present more information there. But we're continuing to work on that integration and also making things more accessible and transparent about how we do that.
Anyone else? Okay, I have one. You talked about making, so all NASA data is available. Well, how do you make it understandable for the non-technocrat community?
That's a great question, and there's a lot of different aspects of that, all of which NASA is working on. I think some of it is, understanding the non-technical community. I think that's one of the things NASA does really well in general with science, is explaining really complex science concepts to the public. But that's less about providing the data than providing the interpretation. And if you look, NASA has a couple of social media accounts focused on climate and Earth, and they're trying to break down some of the Earth system changes that we're seeing and the climate changes and what's going on in a way that's very accessible to the lay public. But going beyond that, we're trying to make things more accessible to other scientists and other people that might use data. Some of it's about, standard metadata, so clearly describing what we have. Some of this is about training. So there are some programs within NASA that train people on using remote sense data for their particular application or satellite data. And then there's also a part of trying to make that data easier to use itself. So not just training, but changing the way we're doing it. So moving some data into the cloud so that you don't need to transfer it to your local machine and you don't need a really big local machine. So there's some efforts there to make data both ready for the cloud and available.
Great, Catherine, thank you very much. We appreciate it.